Okay, we have a nice simple circuit set up here. I've got a power source, I've got a small resistor, which you can see right here. The resistor is connected to a multimeter, which is set to measure current. So we can see that the circuit goes around like this through my resistor into my multimeter, and then it comes around back through this black wire back into my power source. Now, we're going to be interested in measuring how the current depends on the voltage that we apply. So to measure that voltage, I'm just going to move this guy up a little bit. We're going to use a second multimeter that we're going to connect across that resistor. So to do that, we are simply going to connect a voltage probe right there into the input lead of the resistor. And I'm going to connect a second voltage probe coming out of the resistor. So we'll measure the voltage drop across that resistor. Let's see what happens as I do that. Now I'm going to be taking data for this experiment so that we're going to get the voltage and current, and we're going to measure those simultaneously. Then we're going to plot the two of them. And I'm just going to start turning this voltage up. Okay, we'll start at about half a volt. 0.48, that's close enough. And you can see that 0.48 volts will give us a current. I'm just going to change the scale on here so we can see it a little bit better. Will give us a current of about 1.44 milliamps. Now I'm going to increase that voltage a bit. Oops, I'm going to change this one here. I want to go up to about 1 volt, so that's 0.99, which should be close enough. 0.99, and you can see now my current has just about doubled. We now have about 3.04 volts. Milliamps, excuse me. Let's go up to 1.5 volts. 1.51, that's pretty close. And you can see we're at about 4.63 milliamps. Let's go up again. Let's go up to 2 volts. Overshot that a little bit. 2.01 is pretty close. You can see we're at 6.17 milliamps. Let's go up to 2.5 volts. 2.51 is nice and close. You can see we're at about 7.75 milliamps. Now let's see what that actually looks like on a graph. So I've taken the liberty of plotting our voltage as a function of the current for the circuit we had before. And what you can see, there's my voltage in volts. Here's my current in milliamperes. And you can see my data makes what is pretty much a straight line. There's a little bit of fluctuation to it, but for the most part it's a straight line. This is a relationship that we call Ohm's Law, and it's true for many materials. The voltage is proportional to the current, directly proportional, so that if I plot them, you just get a straight line. Now, there's, whenever you write an equation like this, you usually include the slope in the equation. So we need some parameter that describes the slope of this graph. And in this case, the parameter is called the resistance. So we say that the voltage is equal to the resistance times the current. This is Ohm's law. So what is the resistance? What is that slope? Well, suppose for the moment that we had a very, very big resistance, a very large slope. So we went up like this. Well, if my slope were very, very high, that would mean I get a lot of voltage I would need a lot of voltage to just get a little bit of current. In contrast, if my slope were very, very small, I would get a lot of current without having to apply very much voltage. So you can think of the R, again, the R is what we call resistance. You can think of the R, the resistance, as being how much that circuit element resists current. If I have a big slope, that means I need a lot of voltage just to get a little bit of current. If I have a low resistance, a small slope, that would mean there's not much resistance to current flow. I get a lot of current for very little voltage. This is the essence of Ohm's law. Let's see if we can try to figure out the units of resistance. So we know potential or voltage is measured in volts. Current is measured in amperes, which means resistance has got to be, it's got to have units of volts per amp if I'm going to have this equation be consistent. What that means is, we've got another unit here. Usually we like to come up with a shorthand for that. So our shorthand is we define this symbol, omega, as an ohm. An ohm is just a volt per ampere, and an ohm is the unit of resistance. So what exactly is resistance? Well, if I look at a circuit element, some piece of wire or metal or whatever it happens to be that's in my electrical circuit, we have charges that are flowing through it, some current. We're going to imagine them as positive charges flowing through the circuit. That element has some length L, some area A. Now, on a microscopic level, all circuit elements are made of atoms. If I'm sending charges through it, the charges can scatter off those atoms. So that's going to create some resistance for the charge flow through the circuit. If my circuit element is longer, you'd expect that it's going to be harder to get through because it's going to have to travel a further distance. Those charges are going to have to travel a further distance to get from one side to the other. They're going to scatter more. There's going to be more resistance. However, if the circuit element is wider, it's thicker, then you would expect, since there's more area to pass through, you're going to have less problems getting through. There's going to be less resistance. It's kind of like driving down a highway, and suppose there's construction. You constrict the area that these charges have to go through. It's the same as constricting the area that cars have to go through. You're going to build up a traffic jam, and there's going to be more resistance to the traffic flowing. If you give multiple lanes, there's going to be less resistance to the traffic flowing. Multiple lanes is just the same thing as having a bigger, wider area for our charges. So we can write our resistance in terms of the length of the object in the area. We expect to get more resistance as the length increases, so I'm going to put an L here. And we expect that the resistance is going to go down if I give you an area, so I will divide by the area. And there's one more property we need to have. That property is called rho, for resistivity. This is our resistivity. What units does resistivity have? Well, my resistance is measured in ohms. This is in meters, this is in meters squared. So to get ohms out of that, I have to multiply by ohm meters. So my resistivity is ohm meters. Now, what exactly is resistivity? Well, as we've said, my resistance depends on the geometry of the object, depends on the length and the area. Well, it's also going to depend on the material. So a piece of copper is going to have less resistance than a piece of plastic. Materials have a property called the resistivity, which tells us how resistive they are to electric current passing through them. So resistivity is a material property that tells us how likely a material is to pass current through it. The bigger resistivity you have, the more resistive that material is to passing electrical current. Now, here are a few examples that might be of interest to you. So we have copper. Copper is a very conductive metal, so it has a very low resistivity, 1.7 times 10 to the minus 8. About 5 to 10 times bigger than that is iron. Iron, also a metal, but not quite as conductive as copper. But you still have that 10 to the minus 8 there, which means it's got a very low resistivity. Now, let's change up a bit. Let's go over to blood. Human blood, it has a resistivity of about 1.6. So that's much bigger than any sort of metal. So it's not a very conductive material, unless you compare it to something else like muscle. So muscle is about 10 times more resistive than blood is. And body fat is twice as resistive to electrical current as muscle is. So one way, if you're an exercise scientist, if you want to measure somebody's body fat percentage, you can hook up some electrodes. You can measure the conductivity or resistivity of a person's body, and you can use that to figure out how much muscle there is and how much fat there is. It's just a simple matter of figuring out what your resistivity is and then comparing it to the amount of muscle and the amount of the resistivities of muscle and the resistivity of fat. Okay, so we have dealt with batteries, which supply voltage. We've dealt with current, which is how electric charges move around in a circuit. We've dealt with resistance, which tells us how much an electric circuit element is going to push back on the current and try to resist that current. Now we want to deal with some complicated situations. So what happens if we deal with a complicated circuit? So for example, if you crack open your cell phone, you look inside, there's some complicated bit of electronics in there. That's one example of a complicated circuit. Another complicated example of a circuit, let's say I just take a neuron. There are charges flowing in a neuron. There are voltages across the neuron. We've got current, we've got voltages, we've got charges being stored on the neuron. This is a very ridiculously complicated circuit. How do we deal with circuits that look like this? Well, like all of our physics models, we're going to take a complicated real-world situation and try to simplify it by using a simplified model. So we are going to make an abstract version of our neuron, and that neuron is going to be represented by perhaps some symbols. So you'll make a circuit diagram that looks like this. This symbol, which I'll draw again over here, got a long line and then a short line, represents some electromotive force, or EMF. EMF stands for electromotive force. You can think of an electromotive force, it's electro, which means it's electrical. Motive, which means it's pushing things around, and it's a force, so it's pushing those things around. It's basically something that pushes charges around, so you can think of an EMF as just some type of battery. Similarly, we have this other symbol here. That symbol, give myself some more room, that symbol, jagged line, is the symbol for a resistor. So there are parts of any circuit, whether it be the circuitry in your cell phone, the circuitry of your brain, your neurons, we can break it up into circuit elements that push charges around and circuit elements that are resistive to the motion of charges. We could also break it up. I'll use a straight line. That's just an electrical wire. So that would be kind of like a piece of copper. It's something that conducts very well without a significant amount of resistance. So what we're going to do is we're going to use these circuit elements and make an abstract picture of complicated circuits. I have here two resistors. This is just what a resistor looks like. You can see those little colored bands on there. The colored bands are actually a code that tells you what the resistance is. So I could look at the code to figure out what the resistance is, but rather than that, just to keep life easy, we're just going to measure the resistance with our multimeter here. I'm on the 2000 ohm resistance setting, and you can see that I get a resistance of about 329, about 330 ohms. Let's see if I get a better connection, I might be able to get a better reading on that. Yeah, about 329 ohms. And I have another resistor here that's going to work pretty much in the same way. So we're just going to take this guy out, put our other resistor in. Now these should be roughly identical resistors, so they should both be about 330 ohms. This guy's a little bit less, it's about 324 ohms. So that's the resistance of each of these electronics components individually. What happens if I combine the two of them together? Okay, so what happens if I just twist these guys together to make one big resistor? What should my multimeter read for the resistance if I put these two resistors in series? All right, well, let's see what the answer is. If I connect my multimeter, remember they were both about 325 to 330 ohms, and you can see my multimeter is telling me that in total they're about 650. So if I put multiple resistors in series, it must be true that the resistance combined for the two of them is just going to be the sum of the two. Let's see how resistors combine when they're in series. So in the real world, I had two resistors and I connected them end to end. It's my real world picture right there. In symbolic circuit world, I'd have resistor 1 connected to resistor 2. So that's my symbolic circuit. And what we see is that if I'm some charge flowing through that circuit, I have to pass not only through resistor 1, I also have to pass through resistor 2. I don't have any options there. To get from the beginning to the end, I've got to pass through both of them. There's no other path that I can go. Well, what that means is if I have two resistors, my resistance total, what we would call my equivalent resistance, is just going to be resistance 1 plus resistance 2. This is how you add resistors when the resistors are in series, one right after the other. Now let's try a slightly different experiment with our resistors. I still have my two resistors, each of which are between 325 and 330 ohms. I'm going to combine them again, but now I want to combine them in such a way that they're parallel with each other. So right now they're parallel with each other. We're just going to twist them about like this. Okay, so now they're not in series with each other, they're going to be in parallel. Let me just spread them out a little bit so you can see that they are indeed in parallel with each other. And I'm just going to connect my multimeter, and we're going to read what the resistance of them combined in parallel is. So if you had to guess what the resistance of these two resistors is going to be in parallel, what would you say? All right, let's try it and see. I've got my two resistors in parallel. I'm now going to connect them and connect them to my multimeter. And you see something that might be surprising. We actually get about half the resistance. So initially we were between 320 and 330 ohms for my two resistors individually. Now when I combine them in parallel, I get about half that. So if I double 163, you get about 326. So why is it that we are getting less resistance in parallel than we were when the individual resistors were connected to the multimeter? Let's see what happens when we have resistors in parallel now. Well, we say they're in parallel because if I look at my circuit, I can have current going down here, and then that current can split into two parallel directions and then recombine. And in my symbolic circuit, we'll get the same thing. Again, my current can come in this way, and the current can split off and go through either one of the resistors, either through resistor 1 or through resistor 2. We've got two paths. Well, that should reduce the amount of resistance that we have. So that if I wanted to write this as one big resistor, one equivalent resistor, you would say that the equivalent resistance for that guy, well, it needs to be smaller than R1 and R2. In fact, even if one of these is smaller, the resistance has got to be smaller than the smallest one of these resistors, because we're giving it more paths to go. So if R1 was a tiny resistance, most of the current would go through that small resistance, but some of it would still go through resistor number 2. So we've got to have even less resistance than R1. We've got to have less resistance than the smallest resistor that we have in parallel. Well, the way we write that is we say that the resistance is 1 over R1. Actually, let me do this a different way. We will say R1 times R2 divided by R1 plus R2. Another way to write that is to say that it's 1 over R1 plus 1 over R2 to the minus 1. If you work through the math, you'll find that those two are in fact equivalent formulas. And in fact, I prefer this way of writing it because it's a more general method of writing how to sum up resistors in parallel. It's more general because if I have, let's say I have a third resistor here, it's hard to modify this equation, but it's easy to see how I modify that equation. I would just take 1 over R1 plus 1 over R2 plus 1 over R3, and then take the inverse of the whole thing. If I have 4 resistors, I would take 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, and then take the inverse, take it to the minus 1 power. So this is how you figure out the equivalent resistance of resistors that are in parallel with each other. We've talked about what to do with resistors in series and parallel, and we've talked about what to do with batteries in series and parallel. Now what we want to talk about is how the current is going to behave. So how are the current and voltages going to behave in circuits, in complicated circuits? Is there a way we can simplify them? Well, it turns out there's a very simple rule to deal with the current. It's called Kirchhoff's Law for junctions. And there's a corresponding law for voltages called Kirchhoff's Law for voltages. So say I have a circuit, and say I have a wire that branches off into 2 sections. And we have some current flowing down this wire. Got this kind of wishbone shape. And I have current flowing down the wire. Let's say I have current 1 coming into the wire. Well, it's got to be true. Again, since current is just the flow of electrical charges, there's microscopic charges that are going in here. It's got to be true that whatever charges come in have to come out. Right? They can't get stuck in the junction. If the charges get stuck in the junction, that means I'm going to start to build up charges there and they're going to repel each other, and then they're going to push each other out anyway. So what we have to say is that whatever charge comes in, comes out. So if I have I1 current coming in, my current's I1 in, I would have to have the same amount of current coming out. So it must be true, in this example, that current 1, the current that goes in, has to equal the current going out of the junction. If I want to write this more generally, we would say that the sum of the current in any junction is going to be 0. What I mean by that is, you have some net amount of current going into the junction, call that positive current going in. You have some net amount of current coming out of the junction. Since it's leaving the junction, we'll call that negative. If you add all of that current up, you've got to get no current, because you can't have any buildup of charge inside that junction. You can't lose any charge from the junction either. You can't have more coming out than you had coming in. It's a very simple rule if you just think about it in terms of the microscopic charges that are moving around. All the rule is saying is that whatever goes in has got to come out. Now let's consider Kirchhoff's law for voltage. In this case, sometimes it's called the loop rule, because whenever we have a circuit, we've got to have a complete circuit, which means we've got to loop around the circuit. So let's say I have a battery and a resistor. Just a very simple circuit with a battery and a resistor. Say it's a 10-volt battery, so I would say my electromotive force, my EMF, is 10 volts. Well, that means there's got to be a 10-volt jump going from the negative end of the battery to the positive end. Now, one of the tricky things about circuits is that voltage doesn't have an actual, doesn't have an absolute number, an absolute value. So I could say that this bottom end is 10 volts, and if it's at 10 volts, this upper end of the battery would have to be 10 volts higher, so it would have to be at 20 volts. Now, by convention, what we're going to do is, whenever possible, we're just going to say that the negative end of the battery is at 0 volts. So I'm just going to say the voltage right at that point is 0 volts. Which would mean that the voltage at this point is 10 volts. I'll do that in white just to make sure that shows up. So we go from 0 volts to 10 volts. How's that going to work? What happens in the rest of my circuit? Well, we said before that the wires are equipotentials, which means they have an equal potential everywhere throughout the wire. If you're a perfect conductor, which we're going to treat our wires as, because they don't have a significant amount of resistance, if your wires are perfect conductors, then everywhere in the wire has got to have the same voltage. So all this is at 0 volts. 0, 0, 0, 0, 0, 0, 0, 0, 0 volts. Now let's do our other wire. That's going to be at 10 volts. So this is at 10 volts. This has got to be at 10 volts. That's at 10 volts, 10 volts, 10 volts, 10 volts, 10 volts. All the way down over there. The entire upper half of my circuit is all at 10 volts because it's all just one big wire. All right, well, what does that say about what's going on in this resistor over here? All right, well, I know this end of the resistor, this point right here, is at 10 volts. And I know this end of the resistor right here is at 0 volts. So we've gone from 10 volts to 0 volts. So the voltage across the resistor has to drop by 10 volts. That's what the loop rule says. Again, much like the rule for junctions, it's pretty common sense. If you just think, all right, well, the battery pumps up my voltage to 10 volts. Everywhere over here is 10 volts. Everywhere down here is 0 volts. Well, then the voltage drop across the resistor, I'm just going to write it as delta VR, for the voltage drop across the resistor, has got to be negative 10 volts. Okay? It's that simple. All we have to do is look for what the voltage is in each segment of the wire. and I can tell you how big it's going to be using my voltage loop rule. Now that's going to be the name of the game throughout all of our circuits, is using Kirchhoff's laws to find 1, the current, and 2, the voltage at every point in the circuit. So we should be able to find the current throughout the circuit and the voltage throughout the circuit for any circuit that we set up. Now let's do an example that's a slightly more complicated circuit. Here we're going to do 2 resistors in series. We've already done 1 resistor in a battery. Here we're going to do 2 resistors and a battery. Here we go. Well, my goal is to find out the current everywhere in the circuit and the resistance, or the voltage everywhere in the circuit. And I'm going to start off by looking at this end of the battery. And we're going to define the voltage relative to this section. We're going to say that this section is at 0 volts. So that means everything over here is 0 volts. 0 volts, 0 volts, 0 volts, 0 volts. Remember that wire is an equipotential. So every point on the wire connecting those 2 resistors is going to be at 0 volts. So we've already got a good chunk of our circuit figured out. On top of that, we're going to say that this section of wire is all at 6 volts. It's all at 6 volts because I've gone from 0 volts and crossed a 6 volt battery. So the change in voltage has got to be 6 volts. Everything in that blue region has got to be at 6 volts. Now I get to the resistors. Now it's going to be difficult to figure out what the voltage is going to be in that middle part. To help us out, let's see if we can use the fact that these 2 resistors are in series with each other. So I can treat them like one big equivalent resistor. It's just like one big resistor, combining those 2 resistors. And we know that when you have 2 resistors in series, one right after the other, that the equivalent resistance is just the sum of the 2. It's just like taking one big resistor. I have a 1 ohm resistor and a 2 ohm resistor. Therefore, in total, it's going to act just like a 3 ohm resistor, just because you take the 1 plus the 2. Okay. So that's helpful information to know. You know I have a 3 ohm resistance. What does that mean? Is there anything else that can tell me? Well, we've already solved the problem of a battery and 1 resistor. Well, now we've reduced this problem to a battery and 1 resistor. It's just a resistor that's a bigger combination of the 2. And I can use Ohm's Law to figure out what the current is in the circuit. So Ohm's Law says that the voltage drop across the resistor has to equal the current through the resistor times its resistance. In this case, the equivalent resistance. And I know, going from one side of that big resistor to the other, that I've got a voltage drop of 6 going down to 0 volts. So I can solve for what that current is going to be. The current is going to be the voltage drop divided by the resistance. So that's going to be a 6 volt drop divided by a 3 ohm resistance, giving me a 2 ampere current everywhere in the circuit. Why is it everywhere in the circuit? Well, it's everywhere in the circuit because my circuit doesn't have any branches to it. The only path that the current can go is around the loop in a clockwise fashion. So we can just say that our current is going to be 2 amps. 2.0 amps, really. So what is this, though? We still haven't figured out what the voltage is everywhere in the circuit, because I need to figure out what is the voltage in this region that I've marked in orange. How could I figure out the voltage in that region? Well, I know that the voltage at this point in the blue is 6 volts. I don't know what the voltage is here, But I can figure out what the voltage drop from here to here is, because I know the resistance here, and I know the current here. So if I know the resistance and I know the current, I can say, again using Ohm's law, that the voltage drop, I'll call this delta V1 because we're dropping across resistor 1, is going to be the current times resistance 1, which means that that voltage drop has got to be the current, which is, we said 2 amperes, times the resistance, which we said was 1 ohm, giving me a 2 volt drop. Okay. So there's a 2 volt drop going from the blue to the orange, dropping from 6 down by 2, so that voltage has got to be 4 volts. I've dropped from 6 volts down to 4 volts, which means that the voltage drop across my second resistor has got to be 4 volts, because I'm going from 4 volts to 0 volts. Remember, everything in the white is at 0 volts. Is that consistent? Well, let's see. I've got a 2 ohm resistor that has 2 amps of current passing through it. Using Ohm's law again, take the current times that resistance, 2 amps times 2 ohms, I have to have a 4 volt drop, which is exactly how much I need to get across that resistor, going from the 4 volt region to the 0 volt region. So using Kirchhoff's laws and using what we know about combining resistors and other circuit elements in parallel and series, we can figure out the current everywhere in the circuit and the voltage drop everywhere in the circuit. Okay, now let's do one more example, but this time let's consider a circuit where we have 2 resistors in parallel. So what this means is we've got a battery here, a 6 volt electromotive force. We've got a resistor of 1 ohm, and then a second resistor of 2 ohms. But now, our circuit has a junction, in fact it's got 2 junctions, where the current can split. So the current can take different values as it goes from region 1 to region 2 to region 3 in the circuit. Let's start, as we've done before, by setting a base value for the voltage. So just like we did before, we're going to say this point right here is at 0 volts. Okay, right before our battery, just by convention, I'm going to say that's 0 volts, which means all this is 0 volts. 0 volts, 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 0 volt. This is 0 volts because it's connected. All of that is connected just by wires. There's no way for the voltage to change because wires are conductors. Conductors are equipotential, so you have the same potential everywhere. Similarly, as we did before, we have to jump across this battery. It's a 6 volt battery, which means that this point right here is at 6 volts. That means that this is 6 volts, this is 6 volts, 6 volts, 6 volts, all the way around over here, and similarly over here. All of that whole region, all of the top half of my circuit, is all at 6 volts. Well, that makes life pretty easy. Because if I look at my voltage drop in that region, it's 6 volts. If I look at my voltage drop in this region, it's 6 volts. So I can come up with 2 currents. I can say that's I1. And I can say that this current, that current, I'm going to call current 2. We can find out pretty easily what current 1 and current 2 are because, again, we have Ohm's law. Current 1 is equal to the voltage drop, which in this case is just the electromotive force divided by resistance 1. That'll be 6 volts divided by 1 ohm, which will mean that I have a current 1 of 6 amperes. I can also find current 2 over here. Make this a little lighter so it shows up on camera. I can also define current 2 there. Current 2 is the same 6 volt drop, but now it's over 2 ohms of resistance, which means we're going to have 3 amps of current in that region. So I1 gives me 6 amps of current, I2 gives me 3 amps of current, and that makes sense. I'm going to have more current going through the smaller resistor. So if this resistance is half as much as that is, I expect to get twice as much current. What about the current in this region? This region, that's just one big segment. There's no junctions there. I'm going to call this I3. Well, we know from Kirchhoff's junction rule that I3 has to equal I1 plus I2, because whatever current goes into the junction has to come out of the junction. So I3 has to equal I1 plus I2, which will be 6 amps plus 3 amps, giving a total of 9 amps of current. Now that's one way I could have done this problem. I figured out the current in every region, and I have figured out the voltage in every region as well. I want to do one more thing, just look at it a different way. Because we have 2 resistors that are in parallel, and I could, if I wanted to, have treated these as one big resistor, one big equivalent resistor, and I could have written my circuit like this. We've got one big equivalent resistor. How big would that equivalent resistance be? Well, I'm adding 2 resistors in parallel. When we add them in parallel, we expect to get less resistance. And for that reason, we add them as the inverses. So that would be 1 over resistance 1 plus 1 over resistance 2. And then we would take the inverse of that sum. So that would be 1 over 1, which is just 1, plus 1 over 2, which is a half, which would give me 1 over 1 ohm plus 1 over 2 ohms, and a minus 1. And if you work that out, 1 plus a half is 3 halves. Flip that over, you get 2/3 of an ohm. So this equivalent resistance is 2/3 of an ohm. And if we have a 6 volt resistor, we can figure out the current based on that 2/3 of an ohm. I just have to use Ohm's law. Using Ohm's law, I'll just give myself a little bit more room. Using Ohm's law, if I want to find the current, that's just going to be the voltage drop, which again is going to be 6 volts, divided by that equivalent resistance. So that's a 6 volt drop, divided by the equivalent resistance, which we said was 2/3 of an ohm. 6 divided by 2/3, well, that's 9. It will give me 9 amps. Which is exactly the current that I had flowing into that junction. So we have multiple tools at our disposal. We have combining resistors in parallel. We have Kirchhoff's junction rule. We have Kirchhoff's loop rule for voltages. If I use all of those tools at my disposal, you should be able to, if you use all those tools at your disposal, you should be able to figure out the current and voltage anywhere in a circuit.